Good afternoon, everyone, and it's really a privilege and thanks to Professor Dr. Pillai sir for this kind introduction, very kind introduction. So I hope you are enjoying this QT-05, this series, right, lecture series, this course. So there is a lot of quantum computing stuff, and to date, I believe this is one of the best course in India and also globally, because any course, if you see even in academic curriculum or online or YouTube, so they might not be that much updated as per the current the development of quantum computer theory as well as the practical applications. And I hope you enjoyed all the sessions previously taken by Professor Vashwat and Jai Kumar sir, and as well as my colleague Ritojit and all from IBM, and as well as academicians. So, and it's really a privilege, and I'm like honored to take this session. Thanks a lot. So today we'll be talking about the source algorithm, and this is one of the fault-tolerant algorithm. So, and this was introduced much earlier, almost 2 to 3 decades ago. And while we will be talking about source algorithm, the heart of the algorithm is basically the quantum Fourier transform and quantum phase estimation. And today, I won't go hurry. I'll go very slow, and I'll try to go as slow as possible, so that although this is a very simple algorithm, but the essence how this algorithm is a bit different from the classical DFT or FFT. And I shared a material, although I won't follow the material. So because I believe the written form of information sharing should be very different from the information that is shared with you, right? And the verbal information, verbal communication. So this will be a bit different, but conceptual and a bit mathematical, I would say. And I hope you will be enjoying this session. So let's start. So can anyone confirm that you all of you are just visible, can see this my whiteboard, right?
Yes,
So yeah,
yeah,
thanks.
yeah, yeah,
Yeah,
yeah.
yeah. So
But
we
I'm
we
also confirming, yeah.
yeah. So at some point of our engineering study, and I believe many of the students might be from chemistry or biology, even biological science background. Often I have seen their comments on LinkedIn or sometimes in the chat. So let me start with a very naive and a very vague way or naive way or layman way of introducing this Fourier transform. Okay, so I'll roughly take 1 hour 45 minutes, including your questions and all. And please feel free to write your chat. I'll look for each and every query, and I'll try to answer. So basically, the goal of this DFT, that is the discrete Fourier transform, discrete Fourier transform. This person Fourier actually was an engineer, electrical engineer, but this theory, DFT by him, like the Fourier transform theory, both the discrete version and as well as the continuous version, is one of the core mathematical branch right now. And it has many implications in practical application, especially when we try to understand various frequency analysis and in various domains. Even if you are a biological student, so often you do various microscopic experiment and try to understand whether a biological phenomena is repeated over time or how many times it is repeated, or many things. So if you are a chemist or a physicist, often you come across various operators, say position operator X and momentum operator P, and you know they are non-commutative operator. And suppose you are working on certain Hamiltonian, where the combination of both kinetic and potential are there. So now when you try to implement them on a real system, so basically you need to convert either position to momentum or momentum to position. So you need to convert the basis from one domain to other domain, and Fourier transform is one of the tools, right? And one of the major innovation in this DFT theory was an algorithm called FFT algorithm. Mathematically, they are same, but implementation-wise, classically, this particular algorithm normally takes order of n square, where n is the number of data point, where data points you are basically say your time, your information is in time domain, and you are just converting into frequency domain, or your information is in some domain A and you are converting to another domain B. So this is a domain A, and so say I'm writing as a domain A and domain B, and they might not be commutative. So you want to convert your information, so say function of domain A to information function of domain B. Okay. So basically, so if the length of data points, discrete data point in the domain A is n, so this conversion, this functional conversion or mapping by the DFT takes the order of n square number of operation of the complexity. And one of the major breakthrough in this DFT around 1960 or 65, I forgot the exact date, by two scientists, Cooley and Tuckey. Uh, and Taki was an IBM at that time. So FFT algorithm was discovered, and that basically boils down this order of n square to order of n log n, with a very innovative way of implementing this Fourier transform in the digital computer. Okay, so that was a great innovation, and till date we use it in many ways, in many theory, whether it's in computational quantum chemistry, it's many biological process, especially signal processing applications, control application, communication applications, everywhere. Even in the, we talk about 5G, 6G, and there are various massive MIMO and WaveDM systems, So when you design the precoder and all channel, and basically you do the channel encoding everywhere, you can see that FFT is a code tool, right? And right now, we'll be trying to understand the QFT version of this. I believe that if some of you are not from those who are not from the engineering side, they can have a look what is FFT in Google. You can Google it and little bit see. Basically, the primary objective is basically convert information from one domain to other domain if they do not commute. So in order to basically if your information is not clearly visible in domain A, and you want to see whether that information is clearly visible in domain B or not. So for example, there is certain change in time domain is like this, but frequency domain, it can be clear something like impulsive function, right? In which particular frequency there is a peak. So this is a frequency versus amplitude plot, and this is a time versus amplitude plot, something like this. So, and today we'll be looking at QFT, that is the quantum Fourier versions of this. And instead of introducing this theory from classical part, I'll try to introduce this from the quantum part itself, like, because many of you, I believe at least 70-80% of the audience, you already have taken like QT-1, 2, or 3. And I have, and others as well, like introduce the qubits and others information. So let us start from that point. Okay. So let's discuss about two things. So I'll try to introduce this theory from very beginning, so that, like, with a recap, so that you do not need to remember each and everything again and again. So qubits and states. So if somebody asks you to explain quantum theory in terms of quantum computing in 4 sentences, okay, in 4 or 5 sentences, say. Okay, so what are the things? First is the information, that is the qubit, right? And the basis of information here is basically state vector computational basis 0, which is basically a vector 1, 0. It's a column vector, and Kate 1, that is basically 0, 1, right? And this is called the computational basis states. So these are called computational basis states. Computational basis states. This basis is coming from the linear algebra basis states. Okay. And basically where the classical information typically represent by 0, 1, here it is those are just real numbers, 0 and 1. Here these are vectors, column vectors, 0 and 1. So that means basically these are basis means what? Suppose you have a 2-dimensional information, like information you can represent in 2-dimensional plot. So you normally require x-axis and y-axis. Here this can be your Kate 0 and Kate 1, for example, in 2D Cartesian system. And any vector, R vector, you can represent in terms of these two vectors, 0 and 1. If these are x and y, then normally in our childhood we have learned that this R vector can be written as x I cap plus y j cap, right? here in state of this R vector, we write any computational basically state as a vector, basically, which is a combination of, instead of I and j, we write ket0 and ket1. And this coefficient x and y becomes basically alpha and beta, right? So basically, so these are basically computational basis state, means any vector or any quantum state vector you can represent in terms of these two bases, right? This is the first quantum postulate. Second is, if you want to do any changes on these states, I mean, any changes of this information, like this quantum state, like any rotations or anything, right? So, for example, if you want to understand the if it is it is a eigen basis of certain Hamiltonian, and you want to understand the eigenvalue or the observable, like momentum, positions, energy, right? So something that is required are the Hermitian matrices. Here in quantum computer, they are the gates, computational gates, right? And the computational gates are basically matrices. Say, for example, the Hadamard matrix, that is 1 by square root 2, 1, 1, 1 minus 1. Say, for example, X is uh, basically a x-axis rotation gate, or the basically a NOT gate kind of thing. That means if you multiply this X with 0, you will be getting gate 1, right? Or vice versa. So simple matrix vector multiplications, right? So you just take just put it in place of 0, you place this. In place of X, you place this. So basically vector matrix times a vector, right? So so this is the second part, and the third part is basically so third part is basically, if you represent your state as your A times these computational basis 0 and B times the computational basis 1. So basically, if you do quantum measurement, what you will. So if you do quantum measurement in a rank 1 measurement, basically that is a projection, basically projection operation or the inner product operations, right? So between the computational basis 0, so this is basically a dot product 0 and the quantum state psi. So if you multiply 0 vector with this particular quantum state, so 1 and 0 are orthogonal vectors. From here you can see, right? So 1 and 0 multiplication will yield 0. So this coefficient will vanish out and it will give A, right? Similarly, if you measure this quantum state on the computational basis 1, so basically you'll be getting B, right? So this implies that probability of measuring the state 0 is basically, this is the amplitude, and square of this is basically the probability, is the A square, norm A square. Similarly, because A can be complex number here, so let's take norm of A square, and probability of measuring 1 is basically norm of B square, right? And quantum postulate says that this norm of A square plus norm of B square equals to 1. That whatever outcome you get, sum of all those outcome, right, should be equals to 1 probabilistically, right? And this is the condition. All these are coming from the physics side. There is nothing new. All of you are you know these things, right, from QT-01. So there is nothing new. What is new is that this probability, this is a probability equations, right? Like norm of A, if you repeat an experiment and you get n1 times of an event out of n, and basically n minus n1 by n is basically the probability of the next event. So this is p1 and this is p2, right? And if you sum of these two things, you'll be getting n by n, so that is equals to 1, right? This is simple probability law. So the same thing in linear algebra, this is also called, so there are two implications basically. So one implication is, so we'll connect this probability theory to linear algebra so that you can easily connect why things are unitary and all. So implications. So there are two implications from all these four postulates. So one is operations. So any operations I do on the quantum state, suppose this is my quantum state, is a vector, right? Whatever I do, right? So my probability law should not violate, right? That means operations on quantum state, that is the quantum state is say get psi. This is the quantum state, need to preserve operation on quantum state get psi need to preserve norm, and that norm equals to 1. That means probability should be equals to 1. And in mathematics, we know that the matrices which are basically non-preserving, right? Non-preserving matrices, preserving matrices, non-preserving matrices are called the unitary matrices, right? So if there is some basically matrix U, and that I can apply on the quantum state psi, such that whatever I get, right, the norm of this. So if I take the square, right, what will happen? So basically this will be get psi U dagger U and this psi, right? So basically, this is the definition of unitary matrix says that if there is a matrix, right, the condition is such that if the U dagger U equals to identity, or the vice versa, like U dagger equals to identity, then and only then at that particular condition, if that is the identity matrix, only that condition, this and this basically will be equals to 1, right? So the condition for any operation that will act on the quantum state is that that should be basically a unitary matrix, right? Then the trace will be preserved, right? So this is one implication, and by this we can see that there should be some operator which is U dagger U equals to 1. That means U dagger equals to U inverse, and this kind of operator are called the unitary operator. This is the definition of unitary operator. That's why all the quantum gates are unitary gates. Okay. Otherwise, if this is something else, if this value U times this U is something else, say Y, and if Y square Y not equals to 1, right? That means you are getting outside probability definition 0 to 1, right? So this is norm basically. This is not double mod. This is called norm, 2 norm basically. Okay. So if it is a scalar quantity, typically there is a question in the chat. So if it is a scalar quantity alpha, normally we write mod. That means the modulus of that number. And if it is a vector quantity, we typically write as a norm for a quantum state, right? That's a vector, right? So that's typically notation we use, right? Okay. So this is the one implication. And the second implication is, so another thing is, this is also very important thing when we'll be studying the quantum phase estimation algorithm. Okay, so this is like any operator we know that any matrix A, if it has certain eigenvector x and eigenvalue lambda, that is following Ax equals to lambda x, right? And if that matrix is a spatial matrix, right? Spatial matrix. So that means that is a unitary matrix. Then we can represent its eigenvalue, that is lambda of this U matrix, unitary matrices, as e to the power I theta. Okay, e to the power I theta. That means modulus of the eigenvalues equals to 1. That means determinant of all those determinant of this matrix, which is a product of all these eigenvalues. So if the modulus is 1, then if you multiply n number of ones, you will be getting 1. So this is the first implication. So determinant of all the unitary matrices equals to 1, right? All they are basically non-preserving. Second is, for a single qubit, for a single qubit means 2 cross 1 dimension, right? It's basically only it is represented into zero, using 0 and 1, ket 0 and ket 1. So for a single qubit, unitary gates are simply rotation gates, or the rotation matrices. Okay, simply rotations on the surface of the blosphere, So whether it is Pauli X, whether it is Pauli Y, whether it is Pauli Z, and you all know the definition of Pauli X, Y, Z, its identity. So all of them you can simply represent it as the rotation matrix, that is cos theta minus sin theta and sin theta cos theta, this rotation matrix. So for example, suppose this is your quantum state, say psi, and you just want to rotate it to a theta angle to this as a phi quantum state. So basically, you just need to multiply this r theta vector with this. So this is simply r theta times this ket psi equals to the ket phi state ket phi, right? So this is simply like this in a single qubit case. That means a two-dimensional case, right? Whether your this is represented with some x alpha ket 0 plus beta ket 1. So where ket 0 and ket 1 are just two-dimensional vectors, right? So these are the two direct implication that we are getting from these quantum postulates and all. And just I was talking about eigenvector and eigenvalue. So from there, there is one more complication implications. That is eigenvalues and eigenvectors of the unitary matrices are special. That means if there is a unitary matrix U, that all those are quantum gates, and if there is a eigenstate X, and we can represent say U ket X equals to lambda K ket X. Okay, you can take xk for example. It's one of the eigenvectors. So these are the eigenvectors, and this is like the eigenvalue, right? So all this, if it is a unitary matrix, then we can represent lambda k equals to e to the power I theta. And you see, that means what is happening? U xk xk equals to e to the power I theta, say theta k, and ket x xk, right? This is the equation. Now what is happening? So instead of basically estimating the entire eigenvalue, you are only estimating the phase, right? Sorry, you are only estimating the phase. Estimating the phase is equivalent to estimating the eigenvalue, right? So, and even probably I won't get the opportunity to teach the Hamiltonian, to take a class on the Hamiltonian simulation, where you will be seeing that U equals to e to the power minus IHT from Schrodinger equation. But this H is the Hamiltonian, right? And if you write this part here, and then you write the eigenvalue equations, and you can see this H has to something to do with this theta k. Okay, so there is a very deep relation between these two things about the Hamiltonian, original Hamiltonian, and the unitary operator that you have prepared, which are the basically quantum gates, or the combination of quantum gates U, right? So you are basically, instead of directly estimating the eigenvalue of the Hamiltonian, which is the your desired quantity, right? This can be momentum, positions, energy, or frequency, or time, or any other parameter that you are interested out of observable H. So that has to something to do with estimating the phase. That's why this kind of algorithm are called quantum phase estimation algorithm. So will be coming. So most likely tomorrow I'll show what is the circuit, how this is implemented and all. So quantum phase estimation algorithm. Okay. So now there is more. So this is say 3.1 and say 3.2. If lambda x is one of the eigenvalue and lambda y is another eigenvalue of the matrix U, okay, and also say lambda x not equals to lambda y, and they are distinct eigenvalues of the matrix U, okay, that means their phases are different. If lambda x and lambda y, if lambda x not equals to lambda y, then the corresponding, this implies from linear algebra that the corresponding eigenvector ket x and ket y are basically orthogonal. This is important. Okay. So that means inner product of the eigenvectors x and y equals to 0 if they are orthogonal, right? So sometimes there is confusion between these two matrices. One is the Hermitian matrix, and another one is called the unitary matrix, right? Unitary matrix, and these are the heart of this quantum computing, these two matrices. And I will repeatedly use these things for quantum Fourier transform. So if it is a unitary matrix, say U is a unitary matrix, the definition is U dagger equals to U inverse. I mean, complex conjugate of the matrix equals to inverse of that same matrix. This is the definition. So it implies that u star u equals to identity. So basically, dagger is like you can represent dagger or star, whatever convention you want to use. And if it is a Hermitian matrix, if U is a Hermitian matrix, then U dagger equals to simply U. Means complex conjugate of the matrix is itself. So this is the difference between unitary matrix and the Hermitian matrix. And the algorithm which help us to convert the Hermitian matrices or all the physical observable to the quantum circuit representation or the unitary representation is called the Hamiltonian simulation algorithm. Hamiltonian simulation algorithm. So this is outside syllabus, but I have given this at least some knowledge, some basic version of Hamiltonian simulation in the notes, so that some of you might be interested in simulating chemical molecules or biological problems for especially genetic evolution or say, for example, protein folding, this kind of problem. And you need to understand what is a Hamiltonian in the atomic or the molecular level, and how to convert into quantum circuits and all. This will help. Some of the circuit examples also I have given, autorizations and other things in the notes, which might be helpful. So this is all about the basics, okay? And I believe that you have already taught some basics algorithm like Deutsch algorithm or the Deutsch and Josa algorithm, where you have seen that by one shot you can tell the output of a function whether it is a constant or it's a balanced function. Although it's a toy problem, there is no real application. We haven't seen as such any. And you have also gone through Grover's algorithm probably. So heart of the Grover's algorithm, you can also see the application of quantum phase estimation, which we'll study tomorrow. And heart of the QP is QFT that we'll be learning today. So Grover's algorithm, we have seen that any unstructured array, if there is any unstructured array, so the best classical algorithm takes order of n search to basically find the maximum or minimum element of unstructured array, like 1, 4, 13, 2, or anything like that, and you want to find the maximum element, so it takes order of square root n thing. And I hope this is covered. Can you repeat the Hamiltonian simulation process of taking the Hermitian to unitary transformation? Okay. Okay, I'm not detailing this. So there is like my entire PhD on that only, your question, like who asked this? Manshi Raghav. So Professor Manshi Raghav, this is the question I tried to answer in my PhD, and I think many people as well. So Hamiltonian simulation, the basic objective is you have a so basically, if you see like the Schrodinger equations, right? I del t psi t, right? And that is equals to h of psi t. H is your Hamiltonian, right? And if you solve this ODE equation, ordinary differential equations, right, by basically taking independence of the space and time. I removed the space here only in terms of represented in terms of the time. So you will see that the evolved state, like the psi t plus psi t equals to some u times this psi t0 equals to 0 state, right? Psi t0 or psi 0, right? And this u actually equals to the power minus iht, right? This is coming directly from the solving Schrodinger equations. And so basically, if you want to study the time evolution of certain wave function, so you need to understand the how the evolution matrix happens, like e to the power ist were done. But say H is some Hamiltonian and it has some dimension in discrete level n cross n matrix, and e to the power ist, if you expand, there are infinity terms. So there is no physical hardware which can implement infinity terms on a machine, right? So you need some approximate Hamiltonian u tilde, and such that u tilde minus e to the power iht, this is limited within certain error delta, right? And all the family of algorithms which performs this job are called the Hamiltonian simulation algorithm. Hamiltonian simulation algorithm. So in short, we call quantum Hamiltonian simulation algorithm QHS. Okay. So this is the objective. And there are lots of methods like Tata-Suzuki method, linear combination of unitary method, the Taylor-Series method, the quantum signal processing method, qubitizations method. So there are lots of methods are there. And yeah, I mean, this is, I think, one of the core area of quantum computing, and we even do not know which is the best one, right? There are many theoretical models which, in fact, we do not like, we cannot implement them easily on a machine, right? So this is the question, and in this question, I tried to I tried to have my PhD in this area, and just to converting H to U was my PhD. Okay, so so this is very interesting. Okay, thanks for asking this question. Okay, so now so now now let's come back to the original question. Sorry for taking lots of, I mean, huge time for. Am I not audible? Like, can anyone confirm? Yes, audible.
Audible, sir.
Yeah, thanks. Somebody pointed not audible. Yes, thanks. Yeah, so sorry for taking lots of time for the introduction part. Now let's come back to the original question, original topic, the source algorithm, right? And all the things I covered in the classical things might be important here as well. So source algorithm. So what is the problem? Problem is uh, given a function and the function is periodic, which is periodic, given a function which is periodic, find its period. It has many applications. I'm not going to the application part. Okay. So let us take a little bit strict definition, mathematical definition. And the strict definition is if there is two functions fx and fy, or the function at two different points fx and fy, if they are equal, fx and fy are equal for x not equals to y. Okay. And if and only if the difference between these 2 points x and y equals to some constant times p, where k is constant and p is called the period. So for example, we have seen, like, from our childhood, we have seen like sinusoidal, cosinusoidal things, right? Like, for example, the sine wave varies like this. So this is a very bad drawing. Please bear with me. And we know that take to any peak and in between distance, this is 2 pi is the period of sinusoid, right? And the amplitude of the signal varies between -1 to +1, something like that. This is, we have already seen if this is sine theta versus theta, for example. Okay. And we know that here, if we take 2 points x and y, I should be able to represent x minus y mod equals to 2 pi k here. But 2 pi is the period, and k is like the some constant. So I can enlarge the functions to multiple region, and I can pick up all those points. Okay, and I can represent in this way. So this is a very easy problem to find periodicity, right? But suppose the doctor is trying to understand whether the ECG, electrocardiograph signal of a person, is periodic is not. That means there is a healthy behavior of the heart performance. Now, if I ask this question, and let me try to draw a PQRST complex, something like this, although this might not be correct. Okay. And if you take a small snap of this, where say, so this is one part, okay, say PQRST, it might be wrong. I have to check the actual picture. Now, if you check this PQRST complex, and if you take a simple snap, you may feel this is not periodic, in fact, right? But if you take the repetition of the things, so you have seen in the ECG plot, like although you need only 2 or 3 snaps, but doctors repeat the graph, right? It takes a lot of like chain of your ECG graph that you take from the reporting session diagnosis center. It's a long chain, right? So something like this, then again this, so repetitions, right? So now region to region, like whether PQR, this part is repeated over time in the similar flow or not, how much, whether it is truly periodic or it's a quasi-periodic, it's a bit hard. It's a bit hard problem. Okay. So now it can be harder as well, right? So suppose I draw this picture and you can see this. So you can say, okay, this is not periodic. Okay, you take a limited sample and you say this is not periodic. But in fact, if you could take a large number of samples, this may actually repeat in future, right? So it is not always easy that from a limited sample we say something is period or something is not periodic and all. So period finding problem is a really challenging problem for practical applications, right? And how much challenging is this? Is classically, if you want to calculate the period of a function, so it is order of e to the power some constant times n to the power 1/3 log n to the power 2/3. Okay, so this is the classical complexity. So now if n is the number of bits that is required to represent your number or to describe your period, okay, needed to describe your period or number, then classical, even using the classical FFT that helps you find out the period classically, is basically exponential complexity, order of some exponential complexity, e to the power something, right? So it's an exponentially hard problem. Now, quantum version, I'll derive the algorithm, how it works and all, I'll derive it, okay? But let us try to essence. So the quantum versions, that's the source algorithm using the quantum Fourier transforms or the quantum phase estimation. Source algorithm. What is the complexity? The complexity is order of n square log n log n. So this is the complexity of the source algorithm or the quantum version of the Fourier transform algorithm. So, and this is approximately slightly faster than order of n to the power 3. So earlier it was some exponential and now it's polynomial. And this is the one of the first demonstration of theoretically that quantum computer theoretical model is much faster than the classical computation. So by Peter Shor. Okay, so this is the exponential complexity and this is the polynomial order complexity. Okay, so those who are interested to compute the classical complexity of the complexity of quantum Fourier transform, please go through the book by Isaac Chuang and Nielsen. So I may be wrong in the spelling, Nielsen, Nielsen. And the book name is Quantum Computation and Quantum Information. So let me open my camera and show the first page of the book so that when you buy this book, you can, this is the book for this. So here is the complexity detailed analysis is there. You can have a look. Okay. So now, so we can see that there is a huge like different the complexity for computing the periodics is very different in the quantum and that is there in the classical part. Now, what are the reason behind this complexity advantage by this source algorithm? One is the quantum Fourier transform, and basically we will see quantum phase estimation part of this, which is actually used in the source algorithm. And heart of the quantum phase estimation is QFT that we'll be learning today. And the second part that is basically is the modular exponentiation part. Modular exponentiation part. So this part we'll be seeing tomorrow, modular exponentiation part for this source algorithm. So the problem becomes factoring. So the problem of this prime factorization. So there are two things. One, we were looking at period finding, right? And now periodicity say. Now we are talking about prime number factoring. So these are highly related. These are highly related. Okay, so this is this has any application, huge application, but this has security application specifically, or especially in prime number set number theory and all. So factoring, the problem is I'm emphasizing more and more on the problem itself so that you understand essence why it is so important, right? Instead of just directly saying the solution. Solution will come later. So the problem is factoring a number. Factoring a number which is a product of, okay, some part of this lecture is also there in the Kiskit Summer School. So all those who already have taken Kiskit Summer School, they may feel some of the parts are common as well. But yeah, I mean, those are also part of IBM resource as well. So that is a reference of this lecture material. So factoring a number which is a product of, say, two numbers, two prime numbers, is the basis for the security on our computers. So the sets of algorithms that works, that you define a password, okay, and your password basically that's a big number, okay, in when you represent that in bit string, that's a big number, but that is a product of two or more prime numbers, specifically two big prime numbers. And computing what are those two prime numbers is classically exponentially hard. So that means the number of trial that you need to do to basically decode the password, okay, or hack the password is exponentially difficult, and that's the basis of this security. And the RSA algorithm, which is the basically best, one of the best classical algorithms, which basically acts based on this particular phenomena. Okay, so people are right now, those who are on the classical security region, I do not work in this genre. So RSA, so they are trying some sort of different algorithm which does not basically work in this principle. And those kind of algorithm which they call quantum safe algorithm or post quantum crypto PQC algorithm, post quantum cryptographic algorithm. Okay, so which is not RSA. Okay, so RSA is based on basically prime factoring algorithm, and assuming that it is classically exponentially hard, so it cannot be broken. But you have polynomial times implications using the source algorithm. So has serious implications for, so RSA basically there are various types of key like 512 size key, 1024 or 4096. So often used 2048 size key, right? And this is equivalent to how many qubits? So basically 12 qubits, something like that, 2 to the power 12, some 11, 2 to the power 11. But you cannot easily break because there are other things. So had serious implications for security, but it's also not easily possible because all those qubits should be error free or logical qubits. Okay, and huge number of quantum gates required to implement this kind of circuit. So at least present state of the art says that RSA is safe till now. Okay, so accessible today. Okay, so maybe some quantum communication lecture series in QT-06, me or somebody else will tell you more and more on the RSA and other part, how this is like different and all. Okay, so now so this is why actually this source factorization algorithm was so popular and appreciated that time. This polynomial exponential to polynomial speed up, right? And backbone of that is what called the quantum Fourier transform. So I'll pause here for 2 to 3 minutes and I'll continue again. So if you have any question, please feel free to put in the chat just on the introduction part. And I'll derive now the QFT part. Somebody is asking to repeat the first graph, like this periodicity finding graph. This is very easier one, right? So basically we have learned like sine theta, and if t plus this capital T equals to also sine theta, right? So t is the period, and here we can see is 2 pi is the period for sinusoidal signal. So similarly, this is an easier problem, but often practically from unknown number of samples, finding the period between two particular samples is exponentially difficult. Yeah. This is a break for 5 minutes. Maybe we can come back again at exactly 3.
Yeah, thank you, sir. We'll take a break for 5 minutes.
Yeah.
And the basic idea is quiz is open only for today for quiz 1 and quiz 2. Please complete them. This is for those who have taking the quiz for the first time. So around 1150 have taken. So we are happy with that. But about 1300 people have registered on Canvas. About 50 people have not yet joined on Canvas. I don't know the reason. Of course, every time that is like that. 1300 people are there, and about 1180 people have taken, right? 1185 people have taken the quiz. So that's a record number. We are happy, but we want to encourage that most of you should get a certificate. For those who are joining for the first time, the quiz will be like, what do you say? If you get 40% of marks, you will get a good grade. If you get 60% of the marks, aggregate on 3 quizzes, you will get a very good grade. If you get more than 80% across the 3 quizzes, you will get an excellent grade, right? For those who get less than 40%, depending on their attendance, we will give them satisfactory certificate, right? So please try to understand that, and that's why quiz is very important. And next important is attendance, right? So we will take a threshold and we'll see what best we can do. We'll try to give the certificates to as many as possible, right? So we'll take the break while the lectures are adjusted and the new lecture is started. Thank you so much. If you have any questions, you know that I am available on WhatsApp. So you can message me, though we have not opened the main link to everybody. I understand that there is a little bit of inconvenience, but we are addressing all your queries. And if something is not addressed, please message to me. I will do the needful. And Dr. Satyendra Singh Chauhan is there. Mr. Harshit Nema is there. So all of these people you are aware of. So you can send to any one of them, right? So we'll take a 2-3 minutes break more till maybe 3 o'clock, and we'll start with sir whenever he's ready. Meanwhile, we'll change over the next lecture, right? Thank you.